Hi everyone, my name Halim Fatoni. I'm student of Tungha University, Taiwan. It's my pleasure to participate in the International Conference Frontier Computing 2020, and it's my honor to share my research to all of you. First of all, I would like to say thank you to my supervisor, Professor Yang Chao-tung, who have been here to supervise me, and my lab mate Howie and the Christiani and other friends that I cannot say one by one for their support and help during this research. Also for Minister Education of Taiwan that support me for the research fund and scholarship. In this video, I will present about the container-based edge computing use Kubernetes. Today is the era of Internet of Things. Every single day, we are interact with the IoT, where all IoT data will send to cloud server. Because of this phenomena, it was predict in the future that we will have a problem such as lack of bandwidth. So now edge computing concept rise as an alternative for this phenomena. What is edge computing? Edge computing is the concept where we move the computation to edge of the network. For the example, in the cloud computing system, usually we send a picture to cloud server to analyze and send the result back to the edge device. But now, with the concept of edge computing, we can process the computation in the edge devices and send the result back to the cloud server. Because of this process, now we're counting on the edge device to compute all the process, especially when the edge device has many variant and different architecture. So it is important to monitor edge device in the best performance. So in this research, we try to build a system that can monitor the resources changes in the edge device with container-based uh, compared with the traditional base. I will explain some background review for our project. First is Kubernetes. Kubernetes is open source system for automating deployment, scaling, and management of containers application. Kubernetes features, one of the best in the Kubernetes is first, automated rollouts and rollbacks, where Kubernetes progressively rolls out changes to our application configuration, while monitoring application health to ensure it doesn't kill all instances at the same time. If something goes wrong, Kubernetes will roll back the change for our container. Second feature is self-healing, where Kubernetes will restart container that fail. Kubernetes will replace and reschedule container when node dies. And also, Kubernetes will kill containers that do not respond with the user-defined health checks and doesn't advertise to the client until container ready to serve. The last feature is horizontal scaling. Kubernetes will scale our application up and down with a simple command, with the user interface or automatically based on CPU usage. Next is Docker. Docker actually is a little bit like virtual machine, but unlike virtual machine, which creating whole virtual operating system, Docker allows application to use the same Linux kernel as the system that they are running on end. This gives a significant performance boost and reduce the size of the application. Docker also is a tool designed to make it easier to create, deploy, and run applications by using containers. Containers allow a developer to package up an application with all of the parts it needs, such as library and other dependencies, and deploy it as one package. By doing so, to the container, the developer can rest assured that the application will run on any other Linux machine regardless of any customized settings. That machine might have the code differ from the machine used for writing and testing code. Next is Prometheus. Prometheus scrap metrics from instrument jobs, either directly or via an intermediary push gateway for short-lived jobs. It stores all scrap sample locally and runs rules over this data to either aggregate and record new time series from existing data or generate arrays. Prometheus is designed for reliability to be the system you go to during an outage to allow you to quickly diagnose problem. Each Prometheus server is standalone, not depending on network storage or other remote service. You can rely on it when other parts of uh, our infrastructure are broken, and we do not need to set up extensive infrastructure to use it. Next is node exporter. Node exporter act like an agent. It is installed at each device and will collect the metric resources and send the data to Prometheus. Uh, to visualize our data, we use Grafana. Grafana is multi-platform open source analytic and interactive visualization web application. It provides charts, graphs, and alerts for the web when connected to support data resources, and it is expandable through plug-in system, and user can create complex monitoring dashboard using interactive query builder. As visualization tool, Grafana is popular component in monitoring, often used in combining with time series database such as InfluxDB or Prometheus. Next is a DeepStream. We use DeepStream is a streaming analytic toolkit to build artificial intelligence powered application. It takes in streaming data as an input from USB or webcam camera from file or stream over RTSP, and use artificial intelligence and computer vision to generate insight for better understanding of the environment, converting pixel to insight for better understanding of the environment, converting pixel to insight. DeepStream can be used to build a video analytic solution for traffic and pedestrian understanding in smart city, health and safety monitoring in hospital, self-checkout, and analytic in retail, detecting component defect at the manufacturing facility and others. So our objective actually how to leverage the container technologies to monitor the edge device performance. And for system acceptor, this is in the research we divide become two parts. The left side is the master node or edge server, where we install Grafana, Prometheus, where all data will store, and also we implement container base in this edge server. Uh, like we explained before, with the container base, it has a lot of advantages compared with traditional base. And the right side is the edge sites or not device or edge device, where we run some experiment to run object detection application, and then we monitor the process. In this site, we install some library and Docker, and also node exporter that collect the data and send the data to the Prometheus. So we can monitor the performance of each device. This is the software side of the our edge server. In the left side, we base our edge server based on Ubuntu 18, and also we install Kubernetes, Docker, Python, uh, TensorFlow for our training model training, and then Grafana and Prometheus. On the right side is the node device, where we have Raspberry Pi, Raspberry Pi 3, Raspberry Pi 4, Jetson Nano, and Jetson TX2, where we will install DeepStream in the Jetson Nano and Jetson TX2. But in Raspberry Pi, we only install TensorFlow and Python, and also not exporter here. So this is one one result of the installation in the edge server, where we install Kubernetes. There's a lot of pods that support our service. We can see the service alert, service for Grafana, for node exporter, for other service. So we can monitor all the pods are up here and running. Next is this is one of the example, the visualization of Grafana. So in this we can monitor the CPU usage, system load, and RAM, and etc. So in this experiment, we run some object detection. In Jetson family, we install YOLO V3 SSD and faster RCNN. And the Raspberry Pi, we install FGG, MobileNet, and Inception. So in this experiment, we run some object detection. Okay, this is first result, one example. This is result of the monitoring on Jetson Nano TX2 with a YOLO V3. In this figure, we can see the CPU basics, CPU usage. So it's around 20% usage when they run YOLO V3, and then system load only 2.5%, and then for the memory only spend around 7 giga, only around for 7 mega. And this is the monitoring on Jetson TX2 with single shoot detect. So it also same. So we can see in the chart that the fluctuation in for the CPU usage in the SSD. And next is the Jetson Nano when we run faster RCNN. So in this case, we can see from the CPU basics, in only spend around 20% either. So we can show the fluctuation here. And the last is the Raspberry Pi 4. So here we can see FGGNet with FP16. It spent around 15% of CPU usage. FGG FP16 almost same with FP32. Second is inception, almost same. It's on around 20%. And then the last is mobile net. It's the most use of CPU resource in mobile net, FP16, FP32. So that's all. Our system are able to monitor the performance of each device, and with the controller-based system, this monitor system is I will keep running and keep in the best performance. For the future, we will use this monitor system to monitor all our computation, and we hope we can improve something when we run the object detection or uh, another algorithm. And the other one, in the future, we also want to put another function to monitor energy resource of edge computing device. So we hope we can get the best computation, the best performance for edge device. It's my reference. Thank you for all attention. I'm sorry if I have some mistake. Thank you.